Hello. In this video we'll be discussing section 5.4, the distribution of the sample mean. Let x sub 1, x sub 2, all the way up to capital X sub n be a random sample. Again, this means IID, which is short for independent and identically distributed, of the random variable x. So what does this mean? To remind ourselves, 1, the x sub i's are independent. And 2, the x sub i's all have the same distribution or are identically distributed. And that distribution is in fact the distribution of x. So when we think of a random sample, we can think of it as n simulations of the random variable x. So therefore, we'll define two important parameters of interest. The expectation of x sub I, which is the same as the expectation of x, which we'll denote by mu, and the variance of x sub I, which is also the variance of x, is denoted by sigma squared. So we really could put sub x here, but the role of capital X is not important in this section. It's just simply a name to the underlying distribution of interest. So recall from last video, we had two important statistics. One was x bar, which is defined to be the arithmetic mean. Also called the sample mean. So we add up all of our sample values and divide by n. We also had t sub naught, denoted by the sample total, which is just n times x bar, or n times the sample mean. Just as follows. So these are both statistics because they're random variable on our space of samples of size n of outcomes that x is over our sample space. And so also the xi's are also technically statistics by our definition, but when we talk about statistics, again, we're interested in things in the following way. So these are useful to some extent. So we saw last time that x bar is a good statistic for approximating mu. So our first proposition is the following. The expectation of x bar, also denoted by mu sub x bar, recall, is the same as mu. But the variance of x bar sigma sub x bar squared is actually equal to sigma squared divided by n. And so therefore, one can quickly conclude that sigma sub x bar is equal to sigma divided by the square root of n. So the way to interpret this is that we expect x bar to take on the value mu, but as n gets larger, the less and less x bar varies. And this makes sense in the following way, is that if I have a large sample, I would not expect it to vary much from the true population mean mu. So I'd expect a smaller variance. That variance will go to 0 as n goes to infinity. Similarly, the expectation of t naught is n times mu. The variation of t naught, sigma sub t naught squared, is n times sigma squared. Or we have the following. So the sample total seems to vary more as n gets larger. This makes sense because if I'm adding up a bunch of random variables together, you can think of each of those random variables having their own variance. So if we add them all up, we'd expect the result to have a large variance, or the sum of the variance we would expect it to. So we're going to actually show these things in this following proof. So again, to kind of draw a picture of what I was explaining with x bar and x, it looks like the following. Is that with x, if we were to take a particular instance of x, it's most likely or expected to fall at mu. That's the expectation of x, the mean value, if you'd like. But we can see based off of this distribution, I've made x look somewhat normal here, but this doesn't have to be just a normal, but we can see that there's area associated that's kind of spread out, so the variance is somewhat high. The idea with x bar is that mu doesn't change. We still expect x bar to obtain the value mu, but it's more likely that x bar will take on a value that's close to mu as opposed to x. The interpretation being is that if we were to take a sample size of 1, for example, so one particular instance of x, we wouldn't expect that instance of x to necessarily be very close to mu. However, if we took 100 instances of the random variable x, in other words, a sample of size 100, we'd expect the average of that sample to be much closer to mu than the particular instance of x. So we're going to prove this result now. So to begin with, the expectation of x bar looks like the following. So we're going to use linearity of the expectation operator. We technically only show linearity of the expectation operator on two random variables that are jointly distributed. So we have two random variables, they have a joint distribution. We therefore have linearity of the expectation. This can be extended to a joint distribution of n random variables. And we'll use the fact also in this proof that these random variables form a random sample, or our IID. But for now, in the next video, we will talk about the linearity of the expectation operator using more than just two random variables. But for now, we will just use this fact that it is in fact linear. So that means, a little bit ahead of myself, we can factor out the 1 over n to look like the following. So it's 1 over n times this expectation. We can use now the other property of expectation of being linear, that it distributes over sums. Just like so. Well, we were given that the x sub i's are identically distributed. In fact, so therefore the expectation of each x sub I is the same. And it's equal to mu, where mu is the expectation of that random variable x that we're sampling from. So how can we interpret this? This is 1 over n. This sum here, even though I doesn't show up, it's still a sum of n terms. This formula tells us what the ith term looks like. So on the first term, it's mu. So when I equals 1, this expression is just mu. When I is equal to 2, it's just mu. So we continue doing that for n terms. So this inside sum becomes just n times mu, which all simplifies to mu. To prove the expectation of T naught, we can now simply use the fact that T naught is just n times x bar. By linearity of the expectation operator, we can pull out the constant n. And from what we've already derived, this is just then equal to n times mu. So for the variance part, we can use the fact that T naught and x bar are related by multiplying or dividing by n. So for this, it will actually be a little easier to show the variance of T naught. So what is the variance of T naught? Well, by definition, it is the covariance of T naught comma T naught so T naught is just the sum, so the sample total, and a sample total in the second component, but we'll use the index j just to keep these two terms distinct. I could use the index I, but that will get confusing, so I'll call this the index j. So here we're going to use the fact that the covariance operator is a bilinear operator. So last time we showed that for only two random variables, but it does carry over, and we'll talk more about this in the next section. But it's bilinear or linear in each one of these components, meaning the following, is that the sum, the covariance can be distributed over the sum in the first component, giving us the following. Oops. Oh, rewrite that line. So that first component, we've distributed covariance just over the first component. The second component remains the same. Just like so. Now, using linearity in the second component, we get the following. So it's still the sum where I is equal to 1 to n of each one of these terms, but each one of these terms, after distributing the covariance over the second term, becomes just like the following. So we can remove these outer brackets to give us just this double sum. And the idea is that the covariance of the double sum is the double sum of the covariance. So this is using bilinearity of the covariance operator. So let's write this out. So if we look at this, this is a double sum. I'm going to write it in a double array and try to see what is going on. Our first term x1, x1. So let's look at the values where I is equal to 1. So that's where the first term here is where j is equal to 1. For when I equals 1, let's let where j is equal to 2. And we continue doing this up to xn. And then we add to this, we start where I is equal to 2. Just like so. And we continue in this fashion until I is equal to n. And this is where j is equal to 1. I equals n. J is equal to 2. So this is just writing out this double sum visually so that we can see what's going on. So this is a two-dimensional array where the rows represent values of I and the columns represent values of j. So we have not used the fact, we've used already earlier that the x sub i's are identically distributed, but we have not used independence yet. And one result that we saw with random variables that are independent is that the covariance of those random variables must be 0. So in other words, x sub 1 and x sub 2 are independent, so they don't have any linear relation. Therefore, the covariance is 0. In fact, all of these are 0. The only one that's non-zero in that first row is this first term, the covariance of x sub 1 with itself, x sub 1. Similarly, everything falls off except for the term on the diagonal, so x sub 2 comma 2. And this is true all the way up till the end. So we can see that only the diagonal terms survive and the others are all 0 by independence of our random sample. So this can be rewritten as so. The covariance of x1 with itself, this is another way of writing variance of x1. The covariance of x2 with itself, it's variance of x2. Continuing on, the last term is the variance of x sub n. But each one of these is equal to sigma squared. Therefore, the result is n times sigma squared. There are n terms in this sum, and they're each sigma squared. So sigma squared plus dot 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 plus sigma squared n times is n times sigma squared. And so this shows that the variance of T naught is n times sigma squared. To figure out the variance of x bar, we can use the fact that x bar is 1 over n times T naught. Now, as we showed early in chapter 3, I believe, is that one result is that when we pull for the variance, and which can be done using covariance as well, is that constants can't be pulled out, but they can be pulled out and squared. So this is 1 over n squared, the variance of T naught, just like so. And as we've already shown, this is 1 over n squared times n sigma squared, resulting in our result, sigma squared over n as expected. So these two results are very nice. So let's return for a second. So that's the end of the proof here. And this was just using properties of covariance. So the bilinearity of covariance and the linearity of expectation. And what this says again is that the expectation of x bar is still the same mu, but we don't expect it to vary very far much off of mu if we were to take a particular instance of x bar. So that's the idea. So two more propositions, or two more results from this section are the following. It's the fact if we take random samples from a normal distribution. So proposition 2 states the following. Let x sub 1 through x sub n be a random sample. Again, IID, so they are independent and identically distributed from a normal random variable x. So the x1 through xn have same distribution as x. Then it follows that x bar, which again is just the average, or the sample average, sample mean, and the sample total are also normal random variables. Now, a proof of this requires some probability theory, and there's a few ways to do this, either using convolutions or characteristic functions, but that's beyond the scope of this course. So we're actually going to take this one for granted, but this is a very powerful result and not obvious, is that if we have each of the x sub i's are a random sample from a normal random variable, then the arithmetic mean and the sample total are also normal random variables. In fact, this can be generalized, is that if x1 through xn is a random sample of a normal random variable x, then any linear combination of the xi's is also a normal random variable. So x bar and t naught will be normal as long as the random variable we're sampling from is normal. We have another theorem, the central limit theorem, that says that these random variables will always be somewhat normal as we get large samples. So it can be stated in the following. Let x1 through xn be a random sample. So without any assumptions on what sort of distribution they have. Then x bar and t naught are approximately normal distributions for sufficiently large n. So there's some vagueness in here, some gray area. What does it mean to be approximately normal? Well, for us, that's simply going to mean that we're going to assume that they're normal and our results will be good approximations. This really needs to be clarified in a more rigorous course. Again, also sufficiently large is another vague assertion, but for sufficiently large n, we want this to be true. And so the rule of thumb to stick by, which we will stick to, is that a sample of size 31 or greater, so greater than 30, is sufficient for these two statistics to have approximately normal distributions. So usually this is a very conservative rule of thumb, meaning the following, is that in many cases n doesn't have to be this large, especially if the underlying distribution is, so in other words, the distribution of x that we're sampling from is close to normal, or it has normal characteristics already. But this is a conservative rule, which means that it doesn't matter what distribution the underlying distribution is. As long as our sample is greater than 30, these statistics will be approximately normal. So in the next video, we'll be over section 5.5, in which we will talk about linear combinations from a random sample, or IID, and look at some of those characteristics more in depth.